So what I'm going to do here is just give you the very basics, and I actually have grown to start to really like the idea of like what is an NMR. We just sort of nuclear magnetic resonance. What is this? If we can get some concept of what that is, I think that actually helps us understand what we're trying to do here. And I promise you that this workshop is not filled with a lot of math, and I think that most of the math that you're going to see is going to be just in this one or two slides. So but it's useful to recognize what's going on in an NMR experiment. So starting with the nucleus of nuclear magnetic resonance, some atomic nuclei, not all, but many of them have a property that's called spin. That arises from angular momentum in quantum mechanics. And so the spin is the term that we use. It has good reason to be called spin that you'll see in just a minute about what it does what they do in a magnetic field. But a nucleus is the nuclei that we concern ourselves with in metabolomics and solution state metabolomics in particular, spin 1/2. You probably have heard of this in physical chemistry or other areas, but spin 1/2 nuclei, this is like proton, C13, phosphorus 31, nitrogen 15, and several others. So spin 1/2 nuclei can have two different energy levels when they're put into a magnetic field. And the magnetic field, the term for magnetic field is B0 right here. And the reason that they can have two different energy levels is because of this that you can have 2I plus 1, where I is the spin. And so 2 times 1/2 plus 1 equals 2. That's how many that's the rule to describe how many energy levels is possible. So this diagram right here is sort of typical NMR type energetic diagram where outside of a magnetic field, when there's no magnetic field, which is actually pretty much impossible because the Earth is a magnetic field, but outside of the magnet that we're talking about, we'll assume that the magnetic field is zero, and there is no separation between these two energy levels, alpha and beta, so that there's no energy gap. But if you put the nucleus with a spin 1/2 into a magnet that's greater than zero, magnetic field that's greater than zero, you'll get the splitting into a low energy state alpha and a high energy state beta in the presence of a magnetic field. So outside of the magnetic field here, let me get my laser. The energy levels are equal. In the magnetic field, the energy levels are proportional to the magnetic field that you're putting it in. So this energy splitting right here gets bigger linearly with magnetic field strength. And omega 0 is the frequency that you measure for a nucleus. Gamma is the gyromagnetic ratio, which is just specific for a particular type of nucleus, like a proton has a known gamma, C13 has a known gamma, etc. Sometimes you see this equation with a negative sign, really doesn't matter for the purposes of what we're going to be talking about here, but omega is proportional to B0. Okay, so this is a really small energy gap. So it leads to in a magnetic field, the excess of energy, the energy level splitting between the alpha and the beta state are very small, and it's really governed by something called the Boltzmann equation, which is written down here, where we can predict the population of alpha over the population of beta based on this Boltzmann equation. And the sad thing about the reason why NMR has lower sensitivity than, for example, mass spec, is that this ratio of alpha to beta is very low. So if there's no magnetic field, there's no partitioning at all, and they're equally populated. If in a 14.1 Tesla magnet, which is 600 megahertz, this is the ratio that you get, 1.000097. So very slight excess of alpha over beta. And so what you have to know is that every time we manipulate our spins in an NMR experiment, what we can make them go both ways. What was down goes up, and what's up goes down. So a lot of the signal that we would like to measure is actually canceling out because it's almost equally populated. If we go up to 25.8 Tesla, which is the field strength of our new 1.1 soon-to-be magnet in our facility, this ratio goes up to 1.000177. So still pretty small ratio. So you get a little bit, and this is why we pay a lot of money for this magnet but it still is very small ratio, and that's what makes it less sensitive than some other techniques. So that's the nucleus part of NMR. The magnet, nuclear magnetic resonance, the magnet part of NMR, first of all, we have to recognize that the Earth does have a magnetic field. It's around half a Gauss, and you can measure it, and you can actually do NMR on the Earth's magnetic field. So people will do things like look for water under the Earth or oil under the Earth with the Earth's magnetic field. If you go into a hospital and you receive an MRI, chances are good that that will be done either at a 1.5 Tesla or a 3 Tesla magnet, which is those are the standard magnets that are used in clinical settings to, for example, look at your knee that got hurt playing soccer or something. So this thing, 1.5 Tesla is 15,000 Gauss compared to half a Gauss for the Earth's magnetic field. 600 megahertz, this is the 14.1 Tesla that I referred to on the last slide. This has 282,000 times the Earth's magnetic field, so it's getting pretty big compared to 1.5. And then the 1.1 gigahertz, 516,000 times the Earth's magnetic field. So that's getting pretty big indeed. So this is what a magnet looks like. That this one has been sacrificed and just as a demo so that we could see this neat stuff. So that on the inside are the coils that make up the magnet, and then on the inside surrounding the coils is a thermos that holds liquid helium, so they can be superconducting, and on the outside another thermos that holds liquid nitrogen that keeps the liquid helium cold. This is the probe, one example of a probe. This one is tilted towards the magic angle, but the probe goes up inside of the magnet and holds the sample in the strong part of the magnetic field. And then the NMR console that you're going to be actually seeing demonstrated today is both a radio transmitter and a receiver. So the frequencies that we're looking at, 600 megahertz, 800 megahertz, 1100 megahertz, these are radio frequencies. So the way this looks here's this schematic of a magnet, an NMR magnet, and the thin lines represent the strong magnetic field in the center of the magnet. Then the probe goes in, and the probe is set up to deliver a perpendicular magnetic field. So the main magnetic field points up, the probe's magnetic field is in the XY plane, and that allows us to do NMR. So this is the nuts and bolts of the magnet. Resonance, nuclear magnetic resonance. At the frequency, at just the frequency that corresponds to the splitting between that low energy and high energy alpha and beta states, at that frequency, this system will absorb energy, and if you put in radio frequency energy at the right frequency, then the spins change energy level. And what happens when you do that, you're going to see a little bit more of this with John Glishka is going to explain this and show you what a 90-degree pulse is, for example. But you can put a pulse in and excite your sample to spin, and it will start spinning around. It's this precessional motion that gives off the signal that we record in an NMR experiment. So the same mathematics describe an NMR experiment as this gyroscope spinning in the Earth's gravitational field. So if you understand this and play with the top, you'll have some qualitative understanding of what's going on in NMR. So we start our experiment with a pulse, and the pulse is nothing more. I think it's the right comparison is it's like ringing a bell. So I have a little handbell. Um, and I'm not sure how much of this can come over the Zoom, but you can hear a lot of different frequencies in this bell. So you can do this with your own bell, your own thing at home. But when you don't just hear one tone when you hit a bell, you hear a range of tones, and that range of tones is a lot like hitting a pulse in NMR is a lot like ringing the bell. And the signal that we get, so we can hear the bell ring, or we can see a resulting signal is called the free induction decay in NMR. So I'm going to just show you something. For those of you who like records, we're going to hear a little bit of Pablo Casal's. I think that this was playing Brahms, if I remember. So I'm playing this not because I love it. I do love it, but
Art, yeah, I'm not hearing a sound, so.
uh-oh. So John can't hear it. Well, I can hear it. So there's no sound coming through according to it's coming on mine, but so you can listen to this PowerPoint on your own. I apologize. I figured that would go right through. Um, but that record that we just that you will hear some pretty music if you listen to this PowerPoint separately. That record is playing. There's a needle in a groove, and that needle is vibrating back and forth as that groove spins. And the vibrations of that needle following a single track contain all of the sound that we're, whether it's rock and roll group or a symphony orchestra or a person talking, that's represented by a single trace, and that's much like we get from NMR. So the idea here is the analogy is that if this pulse right here, this 90-degree pulse that John's going to illustrate, is a lot like ringing the bell, and then the response of that bell is a lot like listening to a record on a phonograph, which is shown right here. And in this case, what we're doing is we can also add together multiple times this whole thing, and the signal to noise of our NMR experiment will go up. But basically, at the right resonant frequency, we get this sort of time response, and the time response shows this is a little blow up at the very start of this, and you can see that it's complicated series of sines and cosines that are all added together, but this is one recording, if you will. And then we're not very good at looking at time domain NMR data. And what we do historically, ever since Richard Ernst developed this and applied it with Wes Anderson and applied the Fourier transform to NMR data, we can do a Fourier transform to convert the time domain signal into the frequency domain. And so the frequency domain signal is the thing that we most often look at in NMR. That's the thing that this is the same urine spectrum that I showed you before. This is the time domain signal that underlies that this is what we actually measure on the spectrometer, this time domain. And we normally convert it into this frequency domain through the Fourier transform. Tomorrow, you're going to hear an alternative to this that Frank Delaglio and our lab have recently developed called SAND, which will actually analyze and model this time domain signal directly. And we think there has a lot of good advantages. Okay, so let's talk about this signal for a few minutes, and how do we understand what's inside that signal? So first of all, here are just a few more spectra that I'll end with, and this is human urine put into I think it's a 600 megahertz spectrometer in this case. And this is the signal that you record. So I've been showing you up to now this signal, this spectrum here, which is very complicated. But if you just put human urine into a spectrometer, this is what you get. And the reason for this is that the concentration of pure water, the proton concentration of pure water is 110 molar. So this peak right here is water or residual D2O, but there's a ton of water in here. And that swamps the entire signal. You can see a little bit of urea right here. But if we collect the data where we are actually saturating and eliminating the water signal, then and letting all of the other signals come up, instead of just seeing that one huge water signal in the center. So saturation is equalizing the alpha and the beta states. So if we saturate this water signal right here, we're making that alpha and beta energetic difference go to zero, and everything else can come up at that point in terms of our signal. So this is the urine sample, the urine spectrum that we can measure when we eliminate the water with it, in this case with a pulse sequence called NOZ-PR. So how do we get this thing? So first of all, I want to introduce, we mentioned yesterday with Mark Macheski, he pointed out the BMRB database, which is part of this NAN and NMR Hub and NMR Box universe of resources right now. And so bmrb.io is how you get to that directly. And what I wanted to point out is, so BMRB has a lot of experimental data for proteins and other macromolecules, but it also has actual NMR recorded data for thousands of metabolites, small molecule metabolites, and these are extremely useful for NMR metabolomics studies. So this is just one example of BMRB. If you do a search, for example, on in this case NADH, I think this is, or what was this one? Yeah, NADH, and the if you do that search, then you will get all sorts of different spectra. You can get a proton 1D spectrum, a carbon 13 1D spectrum, HMBC, heteronuclear multiple bond correlation 2D spectrum. So I'll tell you a little bit about what 2D NMR is toward the end of this, and then you'll hear more tomorrow and on Friday as well in this, but you get all sorts of different data sets that are freely available. They're real data sets, experimentally derived data sets. They're extremely useful. We use BMRB resources all the time in our lab, and I recommend that you get familiar with it. So I'm just going to use some of these BMRB spectra to kind of give you a sense of how this really complicated urine NMR spectrum is built up from scratch. So, for example, here is alanine that you can get off of BMRB. And what you have in the center is this water, residual D2O, even though they eliminated it, it's not totally gone. And then there's a CH3 group over here, the methyl group, and then the CH group right here, the alpha proton, which is close to 4 ppm. And so that's a spectrum of alanine, and that really allows you, just having this information by itself, it allows you to have you can try to go find alanine. You'll see some of that in the fraction library work that Chris and others are going to present on Thursday. So but you get a little bit more than just these chemical shifts. So these are split. This methyl group is split into a doublet. The CH is split into a quartet because these things are coupled together. This coupling has a huge amount of really interesting information that can give you more information than we normally extract in NMR. We're not going to go into that in much more detail. Here's just another example. Here's phenylalanine reference spectrum from BMRB. So this is really the same as alanine, but there's an aromatic ring up here rather than a proton. And you can see it has a big shift from over here for the methyl group before to up here. And that leads to another change in the CH2s as well. and the CHs. The CH is actually pretty close to what it was in alanine. So this is, so the point of this is that a bunch of these different individual compounds add together. In the case of urine, there are hundreds and hundreds of known metabolites in urine, and they and that's how we get that complicated spectrum. So for the last little bit, I'm almost done, but I want to, as long as this actually works, but we might not hear the sound, I'm realizing, with the problems that we had. Let me just see. Oops. There's a little video, and if we can get this to work, great. If we can't, then you can. Then I would really encourage you to watch it on your own. This is made by Brooker. It's a 3-minute video that describes NMR. Let's see.
Nuclear magnetic resonance is a technique that uses magnetic fields and electromagnetic frequencies to study molecular structures. For high magnetic fields, superconducting magnets are used. Lower fields can be generated by permanent or electromagnets. Samples are inserted in the center of the magnet and are positioned in the NMR probe. So the sample is located at the position of the strongest field and highest homogeneity of the magnet. The NMR probe consists of coils that are used to excite the sample and record signal responses at radio frequency. The basis of NMR is that nuclei behave like microscopic magnets in a magnetic field. They spin around the main magnetic field just like a spinning top. This motion is called precession. The frequency of the precession is proportional to magnetic field strength. Additional local field differences are introduced by changing electron densities in a molecule. A higher electron density results in more shielding and thus a lower local field and lower spinning frequency. In NMR, the frequency of the excited nuclear spins can be measured from the electric current they induce in the coil. Fourier transformation of the time domain signals results in the frequency spectrum, with a signal for each different nucleus. The different frequencies we call chemical shifts, as they depend on the chemical structure of the nuclei. In practice, spectra are measured for all hydrogen nuclei at once, which results in the ethanol spectrum with 3 different peaks at different chemical shifts. Since nuclear spins behave like magnets, they also influence their neighbors. One way this happens is through shared electrons in the chemical bonds in the molecule. We call this J-coupling. Each spin can have 2 states, along the magnetic field or against the magnetic field. As an example, we look at the 2 methylene hydrogen spins, which are chemically identical. They can have 4 combinations: 1 spin down, 1 up, both spins down, 1 up, 1 down, 2 spins up. Each combination has a different energy level and influence on the neighboring spins, except that up-down and down-up combinations have the same energy level and influence. The influence is visible as a splitting of the signal of the methyl group into 3. This is called a multiplet. Likewise, the 3 methyl hydrogen spins split the methylene response into 4 signals. In conclusion, NMR can identify molecular structures from chemical shifts and multiplets.
All right. So I think that is a nice overview, of NMR. I forgot to put this into the slides that are shared on NMR Box, but I have another YouTube video. It's kind of similar level information that you got here and on the Brooker thing. And if you want to find that, it's like a 17-minute video. Search for Edisonomics Intro to NMR. It's on the same channel that these live streams are shared on. Okay, so getting back to it, there are just a couple of slides here, and then I'm going to turn it over to John after after some questions and answers. This is a different NMR spectrum. This time it's of cotton leaves, extracted cotton leaves, that for a study that some people in entomology, Krishna Patel in particular, a graduate student in entomology, is doing in our facility. And I show this because you're going to see some of these spectra. We're going to use the cotton leaf data to show sand tomorrow with Frank Delaglio and what you can do with this kind of complicated spectrum using sand. Chris is going to show what you can do with this on a fraction library on Thursday. So there's a lot that you can do to sort this out, but this is a very complex spectrum, probably more complex than urine, which is often the case with plants. And so that's what we're going to be talking about going forward. I do want to introduce a little bit, that just in one slide, basically in one picture, the 2D NMR. So 2D NMR, where I say ND, because you can actually take this to 3 or 4 dimensions or more, and that's often done in protein structural biology. But 2D NMR is really useful. We're not going to talk a lot about it. We're going to talk about 2D NMR, show you techniques on the last day, but we use 2D NMR in our lab a lot. It reduces overlap in complicated spectra. It provides additional information through correlations in that spectrum, can help you identify molecules from scratch using 2D NMR, and you can use it as a basis to search databases. So Raphael Bruchweiler at Ohio State University has this great resource that I recommend to all of you called Colmar, and we use that routinely in our lab to search spectra. So I'm just going to show you a spectrum. This is called a heteronuclear single quantum correlation spectrum, or 2D HSQC spectrum, carbon versus proton correlation of that same cotton leaf sample. And in this case, you have the same chemical shift range along proton as you had before in the 1D. But now peaks are separated in a second dimension that is carbon 13 in this case, and so this region right here is expanded over here. So for example, this peak right here that shows up at where my cursor is, this is a proton that has a chemical shift of about 0.8 parts per million, and it is directly bonded to a carbon that has a chemical shift of just over 48 parts per million. So we get that's the information that's contained in this HSQC spectrum, and just the information between 2 atoms that are bonded together. But this provides essentially a fingerprint of this organism, of this sample, and if you put this into a database like Colmar, you can get a lot of suggested matches. When Colmar uses databases like BMRB, but it has tools in there to match the data that you get right here with the BMRB databases and other databases. So I just wanted to throw this out there because I want to make sure that you're aware of this 2D NMR. And you're going to hear about processing 2D NMR tomorrow a little bit with Frank Delaglio. So going forward, this is the last slide that I have for this NMR intro. We have 3 main topics that we're going to cover in the last 3 days. This is really meant to be the introductory day for the general information. And they all focus on how do you get information out of a spectrum that's like this urine spectrum or the cotton plant spectrum. So how can you extract accurate individual peaks that can be quantified and statistically analyzed from a sample like urine? So, and when I say statistically analyzed, what I mean is we have a lot of experience in our lab giving data like this to a statistician, and statisticians, if they're not experts in NMR, they don't know what to do with this. And so there's a lot of stuff in here that you need to filter out. We think that sand is an incredibly powerful way of doing that. And you'll see tomorrow how you can you can use this technique, the time domain analysis of NMR data sets, and you can extract out every single one of these peaks as a separate entity in a tabular domain format that we think is extremely powerful to do statistical analysis and deconvolute spectra. So the other question that we're trying to address on Thursday is there a way to simplify a spectrum, for example, like this or cotton leaves, by separating metabolites, and that can be, so these could be analyzed in a more simple format or functionally tested and measured, things like LCMS. And that's the basis of fraction libraries. So there's nothing new in this. In fact, I'll show you how this really is building on a lot of historical precedent from natural products chemistry. But we think we've become convinced that it really helps in a lot of metabolomics studies. So we're going to introduce you to the way we are using fraction libraries in our lab. And then on the final day, on Friday, we want to ask the question, are there alternatives? So we like to use proton NMR because it's very sensitive and abundant, but are there other options? And we will show you that if you have the right probe and the right magnet and the right technology, and sometimes the right sample, that C13 NMR has some huge advantages that we'll highlight on Friday about the advantages of C13 over, say, this proton NMR. So that's the plan for this workshop going forward, and that represents the end of my introductory lecture on NMR and on metabolomics.